hello. Last time we looked at equalities and uninterpreted functions and how we can lead them back, or how we can check them basically if they appear only in conjunctions. This was a pure algorithm without using any fuzz-solving, underlying fuzz-solving. And now we look at if these constraints, equalities and uninterpreted functions are involved in arbitrary Boolean combinations, how we can lead it back to fuzz-solving and use propositional logic and use fuzz-solving to check them. So let us start with equalities first. If you have a formula which has arbitrary Boolean combinations, then of course, even if we restrict to CNF and negation normal form, then we can transform it into disjunctive normal form. So if we would have a disjunctive normal form, then we could apply to each conjunction or method, and we could use the previous one. But of course, it is not very efficient because it may result in an exponential number of cases. This we already have seen as we analyze transformation from DNF to CNF and the other way around. So we will try to search for another solution, which is called, instead of syntactic, a semantic case splitting. What this means we will see later when we see the algorithm why it is called semantic splitting. And afterwards we will use fuzz-solving, the fuzz-checking algorithm we have already got known to solve the transformed proposition logic formulas. So let us see how it works. First, we have only equalities, no uninterpreted functions yet. Assume we have this formula. In this case, this is a conjunction, but could be an arbitrary combination. Then we use ECE as an index to denote that it is only an equality logic formula. And we determine the literals which appear in it. This is x equals y, y equals z, and z does not equal x. And we break it into two sets. The first set contains the equalities, the second the inequalities. And now we can build a graph. We can build a graph. This is called the equality graph, which contains the variables in these sets and contains a dotted line if there is an equality between the two variables, and a straight line, a solid line, if they are unequal. We could also have, for example, between x and z, an equality and an inequality, then we would have both lines. So we could also have, for example, this picture. Can you imagine what is the advantage of drawing these graphs for this formula? What does it help us? I would like to check satisfiability of such formulas. Yeah, so I can go passes which are along equalities. So I will find these equivalence classes, which we have looked also for conjunctions last time. And how can I determine conflicts? Yeah? Cycle which contains what? Arbitrary many inequalities? Yeah, if I have something like x1, x2, x3, x4, and I have here one equality, one disequality, one disequality. Is it a conflict? No. So not arbitrary many, at least one, but exactly one. So the idea is that I have one equality path. Let's say this is now also an equality. I have one equality path. This path here implies, due to the transitivity, that the variables are equal. And this one, this single inequality, states that it is equal. So we have a conflict. Okay, now I have a conjunction here, and if I have a conjunction, actually this is the same as we did with the equivalence classes. We have put all the equalities due to the transition. We made the transitive closure, put them into one class, and checked if there are unequal elements which are in the same class. But now if this is an arbitrary Boolean combination, and I write not the equivalence classes but such graphs, then there is one weakening, namely the equality graph is an abstraction. If I have here the conjunction or here another Boolean combination, the equality graph is the same. So that I have here a conflicting cycle which we will call. That means a cycle which contains only equalities and exactly one inequality. If I have such a cycle in the equality graph, it does not yet mean that my formula is unsatisfiable. Because you see the first one is unsatisfiable because the only solution corresponds to this contradictory cycle. But the second one has a solution. Yeah? So how can we use these E-graphs in checking satisfiability of these formulas? Anyone has an idea? Okay, then we go on. So we already cleared it. An equality path we will call passes with only equality edges like this one. And we will use this sign for the transitive closure. And the disequality path is a path which contains only equalities and exactly one inequality. And we will use this notation. And a contradictory cycle is a cycle with one disequality edge, like here, for this cycle. And we can state that if we have a contradictory cycle, then it is always the case that we have on the one side, so two nodes in this cycle. On the one side we have, let's say here, from x to y, on this path we have an equality, and in another direction we have an inequality path. So we can say the subgraph is satisfiable if the conjunction of the predicates represented by the edges is satisfiable. And the subgraph is unsatisfiable if it contains a contradictory cycle. That means they are not exclusive. Satisfiable means, in this case, the conjunction of the edges is satisfiable. That means that it is not contradictory, and unsatisfiable means it is contradictory cycle. So before we continue, if I have a formula and I have this E-graph, then I can cover all conflicts which are due to the transitivity of equality by finding the contradictory cycles in my E-graph. Yes, if I have a formula, phi, then I could kind of add the transitivity information making use of this E-graph. How? Yeah, I have a formula. Let's say here I had the formula x equals y and y equals z and x does not equal z. Yeah? For this formula, phi, this is the equality graph. Now I would like to use such solving. So I would like to transform this problem to a proposition logic problem. How could I do this? We already recognized that if I draw the equality graph, all possible conflicts are represented by contradictory cycles in the equality graph. So the first problem, if I want to go for proposition logic, I have equalities.
So for each equality, I can create a new Boolean variable, and then, I can add units for sensitivity.
Exactly. So I can say the edges are labeled by propositional variables now, and I can make a Boolean skeleton that say x equals y corresponds to E1, so E1 holds. Let's say B, I do not know the notation, it's used later, B for Boolean, E1 holds, and Y is equal Z, so this is labeled by E2 or encoded by E2, and X is not Z, so not E3. Yeah? And additionally, this is satisfiable. The Boolean skeleton now is satisfiable, but the original formula not. So which information shall we add?
So if E1 and E2 then also E3.
Let's say call it transitivity. So if
In general, one should add all cases.
So I'm sorry for the delay. So what we had is that we can, if you have this example where we had, x equals y, y equals z, and x does not equal z, then we wrote a Boolean skeleton for that, and we can define the equivalent formula, satisfy with the equivalent formula E1 equals E2, and E2 equals E3, the Boolean abstraction, so E1 holds and E2 holds, then E3 holds, and so on for the other cases, and the Boolean skeleton E1 and E2 and not E3. So, and you see, since E1 and E2 must hold in order to satisfy the formula, such solving we recognize that E3 must hold to satisfy that clause, and this is in contradiction with not E3. So we get, using propositional logic and SAT solving, that this formula is unsatisfied. So you could say that a general possibility to check equality logic formulas for satisfiability is to build a Boolean skeleton, to build the equality graph, and to state for each contradictory cycle that if all edges but one hold, that means the equalities for them hold, that the inequality for the last edge cannot hold. This would be sound and complete. But there is some problem. Firstly, this number of possible combinations, which edge is an equality, which is an inequality, can be very large. If we have 3 edges, then now we have 3. If we have n edges, then we can have n possible choice which of the edges is inequality and which is equality. And furthermore, what is the even bigger problem? If I have n variables and I build graphs, how many cycles can it have? Especially inequality or contradictory cycles? Now, if I say that it is a problem, then it is exponential. So let us have a look. Here's an example. How many cycles does this example have? How many cycles? Not runs. This is just something synthetic. It doesn't have a run. So just how many cycles? How many? No? you have on the left one cycle,
this one, on the right one cycle, and you can also define this big cycle.
combining the two. Do I have to encode all three? So assume now I make a kind of whole one. That means here you can see this is an inequality and these are equalities. In this special case there is a special answer. And also in the general case, if I do not take care, I just make the connections, do not know if it is equality or inequality, that is perhaps you think that way. If they are signed, so I see that this is the only inequality, which is the only cycle I have to consider, there is only one. Can here something bad happen? No, because there is no inequality between these. There is no inequality line. So this is just the transitivity of the equality. If one of them does not hold, my formula is in negation normal form, then I know that if this equality does not hold, and it does not lead to a satisfying assignment, then I can turn it to true, and then it will increase the possibilities to satisfy. That means if these two are equal, then the chance to satisfy the formula are higher than if it would not hold. So I can assume that they are always equal. And if these three equalities hold, it cannot lead to a conflict. So which is the only possible conflict for this equality graph?
What does it correspond to? Let us give them names. This is x1, x2, x3, x4, x5. Yeah, so I have somewhere in my formula x1 equals x3, x3 equals x4. This was, I give them name, e1, e2, equality 3, equality 4, equality 5, equality 6. So from equality 1, I get x1 equals x3. From equality 2, I get x3 equals x4. From equality 3, here, I get x4 equals x5. From equality, this is 1, 2, 3, go for, yeah. From 4, I get x3 equals x5. From equality 5, I get x2 equals x3. And equality 6 states that x1 equals x2. And this is the only one which appears negated in my formula. Now that's why here the solid line. All the others appear positively.
So just make any Boolean combinations of these constraints and give an assignment, in which is the only case where this assignment does not satisfy the formula. If the Boolean combination is satisfied.
An example is, let's take just the conjunction. So take the conjunction of all these, 1, 2, 3, 4, 5, 6. That means E1 and E2 and E3 and E4 and E5 and not E6.
Now just the most simplest case, I take the conjunction, which is the only satisfying solution for this proposition logic formula. Now all of E1 to 5 are true and E6 is false. That means these equalities hold and this not. And it is not satisfiable because these three are in a conflicting cycle. That means if E1 and E5 hold, then E6 must hold. Yeah? So the only thing what I should encode
this formula to have the transitivity of
to have the relevant part of the transitivity is to say, for this left cycle, that if E1 holds and E5 holds, then also E6 must hold. Yeah? I could, of course, also add for the right cycle the transitivity relation. But it doesn't play any role. Yeah, if by my formula, for example, let's say 2, 3, 4, I would say it here, for example, not the conjunction, but I would just state that one of them should hold. Assume now that I find a solution. I do not encode the transitivity for this. Yeah, because I see there is no negated formula. Now I find a solution here. And it could be that, for example, I find a solution where E2 is true, E3 is true, and E4 is false, which would lead to a conflict in the equality. But they appear only positively. That means if E4 has the assignment false, then it was also satisfy the formula if I change it to true. Yeah, that means it does not mean that each satisfying assignment of my abstraction would satisfy my corresponding equality logic formula. But if there is a satisfying assignment, then I find it also, then I can extend it to my equality logic formula. Yeah? So here I do not need to encode all cycles, only the contradictory cycles. Especially in this case, instead of 3 cycles, it is enough to encode 1. Is it clear what I'm talking about? No? Okay, let us make a simpler example. I just make 1. This is the equality graph for x equals y and y equals z or z equals x. For example, yeah? Now I make an abstraction. This is E1 and E2 or E3. And since there is no contradictory cycle in my E graph, I do not encode anything. Yeah? Because I said I only need to encode the contradictory cycles to have a satisfiability equivalent proposition logic formula. So I build an abstraction and I do not add anything about the equalities. So what I search for solutions, perhaps I find a solution where E1 is true and E2 is true and E3 is false. Now if I transform back to equality logic, what does it mean? It would mean that x equals y and y equals z and z does not equal x, which is of course not a solution. That means it is not that the solutions are one-to-one, but I only want to have satisfiability equivalent. And since my equality E3, x equals z, appears only positively, I know if there is a satisfying solution for this Boolean skeleton, for which one equality, which appears only positively, is assigned false, then it will be also a solution if I assign true to it. Yeah, because it appears only positively. So this is not the solution, but I can assign true to E3 instead. And I know since E3 appears only positively, if E3 false is a solution, then E3 true will also be a solution. And the corresponding formula is, sorry, this is a disjunction, is this one. And this is satisfying. Yeah, so in order to get one-to-one solutions, I should encode all possible transitive closures in the equality graph. But if I'm interested in satisfiability, then it is sufficient to encode the conflicting circles. So especially if I modify now the example and I make this one negated, And I get now a solution E1 must hold and E2 will be false and E2 will be false and E3 will be true. This would be a solution. If I do not encode that this contradictory cycle leads to a conflict due to the transitive closure of the equality, what would I get? I transform it back and I would get x equal y, or this is not equal, or this is equal. So it would not be a satisfying solution. And actually, it can be, especially if I have a conjunction at the top of all three, that I even cannot extend it. I cannot improve it. Assume we have here now a conjunction. Then the only satisfying solution is E2 is true, E3 is false. And then if I transform it back, then I get exactly the original problem, which is unsatisfiable. Yeah, so if I have a contradictory cycle, then for a solution of the Boolean problem, I do not always get a solution for the original problem. So this is the reason why I have to encode contradictory cycles, because these are indeed those cycles which correspond to conflicts in the equality. And if I have non-contradictory cycles, satisfying cycles, then I do not have to encode them, because though they must lead to a miscorrespondence between the Boolean solutions and the solutions for the equality logic, but for each Boolean solution, I can construct also a solution for my equality logic formula just by assigning true to equalities which appear positively in my formula.
If I have a contradictory cycle and I encode this to the formula, I will always get the unsatisfiable, right?
Yes.
So if I found a contradictory cycle, why would I encode it in the formula if I know that this formula will be unsatisfiable anyway?
Naya, you want to have an encoding which is satisfiable equivalent. Of course, you do not know. But what you want to have is, if it is satisfiable, the equality logic formula, then also your proposition logic formula will be satisfiable. And from a solution for the proposition logic formula, you want to be able to construct a solution for your equality logic formula.
But if I find a contradictory cycle, I can stop there because I have a contradiction.
No, because this is only an abstraction. Yeah, here, this equality graph corresponds to both. So you also want to have a solution for the Boolean skeleton. And for the first formula, this corresponds to an unsatisfiable formula, for the second one, for a satisfiable one. So it does not mean that each contradictory cycle is represented by a conjunction in your formula. If it is represented by a conjunction, then you know, at least if it is a top-level conjunction, you know that you lost. So let's say a conjunction in the CNF. Okay. So, yeah.
If I'm right, you have to solve this Boolean skeleton using a subsolver. And this corresponds to your equality formula?
To the Boolean structure of my equality logic formula?
You said before that you could also put this one into this formula in
the disjunctive
normal form, this equality formula, but that's not good. But you have to do it anyways for your Boolean formula, right?
No, this was, the first statement was I could put it into disjunctive normal form, and transform it to DNF is always exponential. There is no other way. But to use a subsolver, you put it into conjunctive normal form. No, you can use Zeitling's encoding. This we also talked about it. This is linear in time and space on the cost of new variables as many as number of operators you have. But this was a good point. So, but still, we can have some problems with the number of contradictory cycles. First, before we come to the number of contradictory cycles, we can reduce our problem sometimes. Using, see, in this example, if you forget about the left and the right nodes, then you have only cycles. But there might be also some nodes which are not involved in cycles at all. And the basic idea is, since they are not involved in cycles, you can give them any value which fits. And if there is an equality regarding these two, since the line represents equality, you know, okay, we make it true. That means I give just true, the value true to this equality. Since this equality does not appear negated, and my formula is in negation normal form, that means if I give it the value true, then I'm at a safe side. If I find a solution with the value true, it's okay. If I don't find any, I won't find any also with the value false. Is it clear? Just because, let's say this is x1, this is x2, since my formula is in negation normal form, means negation appears at most at the equality side. That means one of these forms will appear in my formula. But it cannot happen that something, this is in a certain formula, and then this formula is negated. This cannot be the case. Otherwise, my formula would not be in negation normal form. So if I have only one of these two forms, then either I have here a solid line or a dotted line, and since we have a dotted line, it means that it appears only non-negated.
And what is the same pair of variables appears in the formula? One is negated and one is not negated?
Then I would have two lines. I could have here also this one.
Okay.
And then I have a cycle, which is not so trivial to see, but then I would have a cycle here, going the solid line there and the dotted back. So in this case, we assume that there are no cycles, so it appears only positively. That means only this form appears in the formula. Now, that means, never mind if it is in disjunction or conjunction. If I assign a value false to it and I find a solution, then it will also be a solution if I assign the value true. Yeah? Because it doesn't appear negated. So giving it a value 2 satisfy the kind of more parts of the formula. So I can just say, okay, I just start with true. And what is about this one? Let's say between x3 and x4. Which value will satisfy the formula more?
False. Only appears negated, but
Yeah. So let us assume we assign here true, we assign here false, and then we can forget about it. So we can assign to all equations that correspond to solid edges and they are not part of any contradictory cycle. Then we assign false to them, and all equations that correspond to dashed, that means non-negated edges, we assign true. And then we can reduce the graph. Let us look at an example to illustrate. I have here Boolean combinations of equations and indications. So x1 equals x2 would result in this edge. X1 equals x4 would result in this edge. X1 does not equals x3. And x2 equals x3. Yeah, this is the graph. Now how can I reduce it? According to the previous lemma.
We assign 2 to the equality
So this is true. And the formula can be reduced by assigning true to the equation x1 equals x4. This is this one. So if I assign that true to it, then you see that the first clause, there's a disjunction true or something becomes true. So this part becomes true. And I get something more simple. And now I can build a equality graph for this more simple formula. And I can reduce it again. What can I do? I have one which is an equality, so I assign true to it. I have this equality, I assign false to it. I put these values into my formula. I get not false or true. Even without transformation, I got the satisfaction of this formula just by reducing. So assuming the following, that if we have an equality graph which has some nodes which are not in cycles, especially not in contradictory cycles, then I make this reduction, so I remove them. And I reduce the graph. Of course, it does not always end up in a satisfaction value, but at least in a formula which has an equality graph such that each non-contradictory cycles are removed. And each simpler ones. So we have here in this example, perhaps I was a bit fast, we have seen that we only need to consider simple cycles, simple contradictory cycles. Yeah, first we have seen that we only need contradictory cycles. And secondly, for non-simple ones, for example, this big one is also contradictory. But for each big one, there is a smaller part which is contradictory and which is simple. Simple means that one node does not appear twice. For example, this cycle would contain x3 2 times. Okay. So assume we have only take care of formulas. We assume that our formulas are reduced this way, so the equality graph contains only contradictory cycles. Now we look at how we handle these formulas. We transformed the equality logic to proposition logic by encoding all edges with Boolean variable, all edges in the reduced equality graph. Like here, we had this equality graph, then we add a name to each edge. This names a proposition variable stating whether the equality holds or not. We build this Boolean skeleton, and we add the transitivity information by adding the implication that if two of the edges hold, then also the last one must hold. And we check this conjunction. Good. But still, what is the complexity of this transformation? Note that for each cycle, we do this. You can still say each contradictory cycle, because the non-contradictory, so the satisfying simple cycles, we also already removed by reduction. So all simple cycles are contradictory. How many?
So if we have exponentially many cycles, then we have exponential loss by
Exactly. Can we have exponentially many cycles? Yeah. First, we observe that we need to consider all simple cycles. So, for example, here we had here cycle 1, we had here cycle 2, and this one was cycle 3. So we need to consider only cycle 1, because this is simple and this is contradictory. Cycle 2 is not contradictory and cycle 3 is not simple. But still, if we consider only simple cycles, there still might be exponentially many. Sorry, I go a bit farther here. You can see a good example that there are exponentially many cycles, simple cycles. For each of these components, you can decide whether you go up way around or down. So for here you have decisions and so on. If you have n components, then you still have 2 to the n cycles. And if the only inequality is here, and the other, this one, is an inequality, and all the others are equality, then you have 2 to the n contradictory cycles. So what we can observe is that in this example we have also 3 cycles. Yeah, we have the one here, and the one going around. So what is the difference? Actually, all 3 are simple. Nevertheless, I do not have to encode all 3. Why?
If we include 1 and 2, the transitive constraints of 3 are already included.
Exactly. Yeah, what does it mean? Give them names. This is x1, x2, x3, x4. Then for cycle 1, we have the transitivity between x1 equals x2, x2 equals x4, and x4 equals x1. Yeah, if 2 of them hold, then the third one is implied. For 2, we have x2 equals x4. This is this line. This line is x3 equals x4. And the last one is x2 equals x3. And what would be the number 3? Circle would contain exactly the one which are inside, but not the x2, x4 constraints. So without this one and this one, but exactly this one connects the two. That means if I know that, for example, x1 equals x4 and x2 equals x4, then it implies that also the last one holds. So if I know that 1 and 2 holds, so for 2 of them imply the third one and 2 of them imply the third one, then I also know that 3 of these 4 imply the last one. Yeah? For example, if I know that these 3 hold, then by the 2, I just write it down. So if I assume that, for example, that these 3 hold, yeah? Then I know by 2 that due to transitivity also this one holds, and by the encoding of 1, I know that also this holds. Yeah, so if I have the transitivity for cycle 1 and cycle 2, then I get the transitivity for the fixed cycle 3. So what is now the relation of 1, 2, and 3? Can I somehow formalize it? Which kind of cycles I do not need to encode? Here you can already see that it is sufficient to constrain, that means to describe port-free simple cycles. So what can be a port-free cycle? This would be cycle 3. What is typical for 3? Now we have here an example where we have 3 cycles, and if I encode 2 of the cycles, I do not need to encode the third. Yeah? Can we now make something more general statement, description of such cycles which I, like 3, which I do not need to encode? What is the condition not to be forced to encode a cycle in this case?
All edges are contained in a union of other cycles.
Yeah, this is a good description. A bit, perhaps, more kernel or smaller description would be that if a cycle has 2 edges which are not beside each other but they are connected, yeah, two not neighbored edges like x2 and x4. They are not connected in this cycle directly, yeah, but there is a transition between them. Then it is not chord free. So exactly these edges, this kind of edges are called chords. And if I have a cycle which is chord free, means that there's a cycle and I have edges on them. These are the vertices in the cycle. Then I do not have any shortening connection then going around the cycle. So if I have something chord free, that means without such shortenings, then I have to encode them. But if I have a shortening in between, an edge between two non-neighboring vertices in the cycle, then I do not have to encode it, because this chord distinguishes this big cycle into two sub-cycles, and if I encode both sub-cycles, then this encoding already includes the encoding for the big cycle. Okay, so we do need to encode only simple cycles, and we do need only to encode chord-free simple cycles. But still, there are exponentially many, as you see in this example, because all of these are chord-free. So if I go this way, then there is a connection between these two, namely going the other way around down, but this is not a shortening. This is not just one edge, but these are two edges, like the up way. So these all 2 to the n cycles are simple, no this repeated, and they are all chord-free. So what we do is we can nevertheless also in these cases reduce the complexity by adding chords. That means I add new edges to my equality graph. I cannot destroy anything by new edges, but because I just allow more. That means if I would draw here some additional edges, I would just allow these equalities to appear in my formula, but I do not make anything wrong with it. Yeah, I just kind of weaken my assumptions about the formula and allow more formulas to be represented by this graph. But now what happens to the chord-free cycles? How many are now there? How many? Yeah. So here,
the upper half, the lower one, and
one. Exactly. So I have one big. Here, there's one cycle, and I have here for each lower and upper triangle. Okay, so we will add edges and make a graph model. How it happens, we can look at this example. So we have this big cycle. Then we go along the vertices recursively. That's the first one. And if my cycle is not elementary, that means it contains more than 3 vertices, then I just add a new chord. And then I take the next vertex. If the cycle is still bigger, if it contains a non-chordal cycle with more than 3 nodes, then I add a new edge. And so if I take this one, then I do not need to add new edges anymore, because this cycle are both have only 3 vertices, and the other cycles in which it contains is chordal. So, and now in this case, though I would have had only one cycle, now I have 3, but it is only linearly more. And in case I would have had exponentially many simple cycles, now I have only linear or polynomial in the number of nodes. Okay. So we have seen that I just said, forget about the polarity of the edges, we just now look at the connectivity graph in the equality graph. But if we look also at the polarity, if each equality appears only positively or only negatively, then we can see, for example, in this simple contradictory cycle, it would be sufficient to encode this implication. Why? The other two which I could write down is E2 and E1 implies E3. And E3 and E1 implies E2. Why do I not need to do this? I know that E2 appears only positively and E1 only negatively. That means if I find a solution where E1 is true, then also there is a solution where E1 is false. Yeah, because it is more satisfying. E1 appears only negated in my formula. So that's why if there is a solution where E1 is true, then there is also a solution where E1 is false, and then this implication is automatically valid. Yeah, so I can encode this. Then it will be easier to find from the solution of the propositional logic formula to find the solution of the equality logic formula, but for satisfiability equivalence, this is not necessary. This is because of the monotonicity of the negation law. Okay. So, now we know how to solve equality logic formulas, arbitrary combinations of equalities. Now let us try to formalize an algorithm. So as input, we have an equality logic formula that is a Boolean combination of equalities in negation normal form. And what we would like to have is a satisfiability equivalent proposition logic formula. So what do we do first? We have these several steps. First, we constructed the equality graph. Yeah? But we can say, okay, we construct the equality graph. This has implies a certain abstraction for the equalities, and using this abstraction, I can encode the Boolean skeleton. So, for example, if I have, let me make just an example, x1 equals x2, or x1 equals x3, and x2 is not equal x3 or x2 x 1 2 3 2 I take 4. So I construct the equality graph, and now I take without polarity. So I just stay where there is a relation between the formulas. So between 1 and 2, between 1 and 3, between 2 and 4, and between 3 and 4. Okay, I generated the equality graph. What do I do next? I already told it at the very beginning. Okay, I name the edges. And then each name corresponds now to the statement that the two variables which it connects are equal. So E3, for example, encodes that x3 equals x4. What do I use this graph for? Why did we construct it at all? To find the conflict due to the transitivity of the equality. And we have seen that these conflicts correspond to contradictory cycles. Or if I take an equality graph without polarity, then just the cycles. We have also seen that we do not need to consider all cycles, only the simple cycles and the chord-free simple cycles. And since there are exponentially many in worst case, we made from chord-free non-elementary cycles which have more than 3 nodes, we added new chords in order to get all the cycles with at most 3 nodes. Then we know that we have to encode only polynomially many cycles. So in this case, for example, I could add an edge here between 1 and 4, and I would be done. Now I have only polynomial many cycles for which I must state transitivity. And if I add transitivity for this cycle and for this cycle, for all cycles with at most 3 elements, then it will imply transitivity for all other cycles too. Okay, now I only have to encode it. I have 2 components, first the Boolean structure and then the transitivity constraints. So for the Boolean structure, what would be the Boolean structure of this formula? Just using these Boolean encodings for the equations.
E1 or E4 and not E2 or not E3.
Okay, this is this Boolean structure. And what is my formula for the transitivity constraints? Now, since I have an equality graph without polarities, for each cycle with 3 nodes, I have to add all 3 implications because I do not know, according to the graph, which are contained in where. So let us look at the upper cycle. It means if E1 holds and E2 holds, then also, I give a new name, E5 must hold. And if E2 holds and E5 holds, then also E1 must hold. And if E5 holds and E1 holds, then also E2. And now for the lower cycle, if E5 holds and E3 holds, then also E4. And if E3 holds and E4 holds, then also E5. And if E4 holds and E5 holds, then also E3. Yeah? Okay, I make the conjunction of these two, the Boolean skeleton and the transitivity constraints. I check it for satisfiability, and it is satisfiability equivalent. That means if I get a solution, then I also have a solution for my original formula. And if I find out that it's unsatisfiable, then also the equality logic formula is unsatisfiable. Okay, now we did an example. Let us try again to make an algorithm. So as input, I get an equality logic formula. What do I do then? Nobody? Perhaps it's the question easy. So first, we make the Boolean skeleton by replacing each equality by a fresh Boolean variable. Then we construct the equality graph, start here, and label the edges by our Boolean expression variables. Then make our graph ordered. That means if there is a cycle, simple cycle, with more than 4 elements, then I add a new chord. And then we generate the transitivity part of the formula, in which for each triangle we add the three implications. That means if two edges of the triangle correspond to valid equalities, then also the third edge must hold. And we return the conjunction of the Boolean skeleton and of the transitivity. Okay, and then we can use the
You have the point make the graph causal. We need to check for simple cycles with more than 4 nodes. How do we check for it? I mean, how do we find cycles in general at work?
This is just simple forward reachability. So if you go here, you have one node, and you would like to know if it is contained in any cycle with more than 4 nodes. Then you just go from here forward and make a counter. Now 1, 2, 3, 4. When you come back with counter 5, then you know that there is a result test 5.
Don't we have to do this for every node in worst case?
It is linear in the number of nodes. So it doesn't really work. And furthermore, if the graph is reduced, this is another point. It said that if you have for polarized equality graph, you can remove the non-contradictory cycles, and you can also remove those nodes which are not part of any cycle. So if you have now a graph, then you know that each cycle is contradictory.
Yes, but we have to check whether a node is in the cycle or not once again. So
yeah, but it is linear. I mean, if you go through all nodes, then you know you find even the longest cycle. It is linear in the number of nodes. Yes, it can be simplified to polynomial time. But the other argument is that we know that this graph, which we have checked, contains only contradictory cycles if it's polarized, and that it is reduced. That means each node is part of the cycle. In this case, you only have to check its neighbors. If they are not connected, then you know that it is part of the cycle with larger than 3 elements. Because it is part of the cycle, and if the neighbors are not connected, then the cycle must be larger than 3. Yeah? Is it clear?
actually, if you have this high structure, then if I take the center node and the right on the down right and down left.
This one?
No, with the 5 nodes. Yeah, this one. If I take the center node and compare to the right and to the left, then they are not on the same simple cycle. But still there are neighbors that are not connected.
Yeah, but actually it can. Let me think. So at least you can look at all neighbors. So if none of the neighbors are connected, then you know definitely that it is not. And if you have several nodes, then you can just take 2, and if you add their accord, then actually you cannot make anything wrong. Perhaps if I add here 1.
But if you always use this, is it still
if I have to combine them, I must think of.
From each node you can look at every outgoing edge and look if you can come back to the node only after more than 3 steps. And this way you should find something.
Actually, you can check. Yeah, if you can come back in 3 steps, then you know that you do not need to have the 4 for one of the cycles.
So if you can do it, you can complete the exposure, right? When you start with a node, just look at one successor,
So
the
you
next
can,
two successors, and then you can decide whether from this one you can return back to the first one because it's already completed the transitive closure. And if there is no, if you can, but there is no direct edge, then you add it first.
so even if I make it fully connected, yeah, I get n square mu at it. It is still polynomial, even in worst case. But finding cycles is, so for example, you can do search for shortest passes. And then if you do not find any shortest pass of length 3, then you know that at least each cycle that goes through it is larger than 3. If you find the shortest path of length 3, then you can just remove those and check the rest, again for shortest path. Then you always, if you find that the shortest path is longer than 3, then you just make a port and check again. And if it is of length 3, then you remove those nodes and check again. Yeah, then in this case you would indeed check all cycles in which the node is involved, in which you are. And shortest passes, especially k shortest passes, can also be found in polynomial time. But as said, even in worst case, if you add all possible edges, you are still on the safe side. That is on the polynomial side. Do you have any further questions with equality logic transformation? So, again, if I have a formula, equality logic, arbitrary combination of equalities, I make a Boolean abstraction of the Boolean structure, and see this is an over-approximation. I encode the transitivity of the involved equations, but in order not to have exponentially many, I build the equality graph and make it further such that I have to encode only polynomially many transitivity rules. Good. Then we said also we have uninterpreted functions. And now we will add uninterpreted functions in the arbitrary Boolean combination, and we will lead it back to equality logic. And then this equality logic formula we can again transform back. This we transform to equality logic, and this we transformed already to proposition logic. Yeah, so this we already done, and this is now what we do next. So there are two possible reductions, and we will only look to Ackermann's reduction. And this looks as follows. First, assume that we have an input formula. This is again a negation normal form. It contains infinities and uninterpreted functions. That means functions which are congruent, but I do not know the exact meaning. I only know that they are functions. And if we do it similarly to equality logic, we will transform to satisfiability equivalent equality logic formula, where we have a flat part encoding the Boolean structure of the formula, and a part like we had a part for transitivity for equality. Here we will encode congruence. And we make a satisfiability check. And for satisfiability, as for the equality logic, we have that the Boolean structure must hold and that the uninterpreted functions are functions. If I would like to check validity, then this would be a bit stronger. This would say that if the congruence holds, then the Boolean structure would hold always. This we did not discuss for equality logic, but you can see this was the structure of our proposition logic formula for equality logic, and this looks like this. The conjunction, because also there we check for satisfiability checking, and we also look at this now. So we would like to have a satisfiability equivalent equality logic formula for our uninterpreted function. Do you have any ideas how we could do this? So we have now uninterpreted functions, similarly like equations, but now it is not equations and then an arbitrary function. So let's say we have, previously we had x1 equals x2 and x2 equals x3, or x2 equals, doesn't equal x4, I don't know. And then we made a Boolean skeleton. Now, if I write it as in a pre-notation, then you see that equality can also be a function. An uninterpreted function would abstract away from its meaning, it would mean I just would write something like this. But the result of the function is in this case Boolean. That means these are predicates. Yeah, this is a Boolean function with a Boolean value. If the value of the function is not always Boolean, but it can be arbitrary, then I would have equalities using uninterpreted functions. That means I can have expressions something like f of x1, x2 equals x3, or also nested like f of g of x3, x2 equals 5. So you see there is a relation. Here we had the special case that was equality, and encoding that this is an equality relation, we already encoded also congruence. Now we have, first we abstract away from the meaning of equality, we abstract away that it is an equivalence relation because it must not be, it is just a function now, so we make it deeper. And the same that we did for equalities, now we can also do for uninterpreted functions. So firstly, we just make a Boolean skeleton. In this case, in this example, at the bottom, we just have equality A holds and equality B holds. Yeah? And now I have to encode congruence. That means for each function application, pairs, I say if the arguments equal, then also the function values are equal. For example, here, if f is applied to x1 and x2, and f is applied to g of x3 and x2. Now, if x1 equals g of x3 and x2 equals x2, then x3 equals 5. Yeah, this is progress. And this I have to do basically for all possible pairs of applications of f. So the algorithm which we will do is the following. First, we kind of identify the instances of function applications. In this example, I will call this the first application of f, and this will call the second application of f. Then I build a Boolean skeleton where I replace each application occurrence of my function f by a fresh Boolean variable. This was like a variable e for equalities.
But it's only a Boolean variable is our domain.
No. Here, x1, x2, x3 can stand for any domain. And also the value of the function is, for example, here 1, 2 can have any domain. F of x1 and 2 is the same domain as the domain of x3. So it must be type correct, but it doesn't have to be Boolean. But equality is what it lifts to the pure Boolean. So
yes, but the small fi, don't I replace f of x1, x2 by a new variable f? Is that what the algorithm says?
yeah, but they are now inequalities, so they are not Boolean. This I replace by Now I replace this by F1. And this I replaced by F2.
Yes, but then F1 should be from our domain, not Boolean.
Not Boolean, yeah. But so what I did previously, I replaced the equations by Booleans. Yeah?
But here, if you say F1 equals x3, F1 should be from the domain of the variables. Because
Yeah.
and if you go to the next slide, it states that F1 is a Boolean variable.
Oh, sorry. No, this is wrong. Its type is the domain of F. So if F is a function dn to d, then the type of F is also d. Yeah. Thank you. So we replace each occurrence of a function by a fresh variable, same type correct. And now the Boolean abstraction does not abstract away from the predicates, but from the functions. That means we say that for all possible occurrences of a function f, for two different applications, we say that if the arguments are the same, then also the function values are the same. Let us come here back. So first we abstracted away by replacing these two occurrences of f by new variables, new terms. And then what do we have to state here for the congruence? So this is now this flat. And now we have to build this congruence. What is the congruence for this example here below? Exactly. And if I have several, I have only have two applications of F. If I have more than two, then I have to do for each pair, but I can, of course, give a very symmetric application.
What if F is nested?
Then each nested part is one application. So let us make an example for this. F of x1, x2 equals f of
Decide for one number. So the nested F only has one argument.
yeah. 1, 2, 3, yeah. F of 5 x1. So now I replace each application. F1 will be, let's say we go from inside out, is f of x1, x2. The second application is f of f1, x3. And the third application is f of 5x1. So the congruence, or the flat formula is f2 equals f3. That's all. And then now I apply congruence for the applications. That means if I say for the pair 1, 2, if the operands are the same, then also the function values are the same. So if x1 equals f1 and x2 equals x3, then f1 equals f2. Then for another pair f1, f3, I add the parameter x1 equals 5 and x2 equals x1. then also the function values are equal. And the last one is the 2, 3. Means if f1 equals 5 and x3 equals x1, then f2 equals x3. Yeah? So I encode this congruence, and it is sufficient to apply it recursively to all applications of the same function, excluding symmetry, and then we end up in this algorithm. Is it clear? Okay. So here we have one more example. This is, yeah. You will also have some more example in the exercise, but you can also look at this at home. We did now another example. And next time we will do an application, a very small application for checking equivalence of two methods. And then we will continue with the lecture.